Good morning, everybody. Good morning. Thank you for being here so early, and it's a great honor to open this Earth and Space Science information stream this morning with a double bill on recent advances in deep learning and data analytics in Earth, atmospheric, and planetary sciences, deep learning to solve geoscience challenges. We will have 2 oral sessions filling all of this morning with the coffee break in between and then a poster session. The other honor is that this first session will also be recorded and broadcast, and you will have it on YouTube in January. That's what AGU promised. I hope that everything goes well. There have been some disruptions. People have experienced traveling here. I hope everybody of our speakers is here. And without further ado, I would like to welcome our first speaker onto the stage, Victor Pankratius, to speak on deep learning for discovery of atmospheric mountain waves in MODIS and GPS data. Thank you.
Thank you, Jens. Good morning, everybody, and welcome to AGU. This is the first session, and today I want to present to you our work on deep learning for the discovery of atmospheric turbulence, in particular mountain waves, lee waves, where we're aiming to leverage MODIS and GPS data. And this is joint work done with my postdocs, Justin Lee, Cody Root, Michael Monlock. Maybe now I should say a new faculty and new fellow, and with Thomas Herring at MIT EAPS. So let me give you a little bit of context. We're looking particularly at airflow over uneven topography, which can create lee waves downstream of topographic features. And if you've ever been on a plane, maybe on your way to AGU, and you look outside, you might have seen these ripple patterns. And these look pretty, but in principle, they can be hazardous to aviation. So there's a real importance to understand where these patterns form and why, and track them over time. And in this work, we're trying a new approach to fuse information from 2 different sources, which we haven't seen really being done before. One is information from NASA MODIS imagery, which actually uses satellite imagery to look at the cloud patterns that are formed. And the second source is GPS signals from the Plate Boundary Observatory. And in particular, I will show you that there are outlier patterns that we believe are due to this turbulence, and there has been a study that pretty nicely shows that there is a correlation between certain outlier patterns and lee wave turbulence. So the work I'm going to present you today is a first attempt to address this problem with neural networks and this kind of data fusion. So we're focusing on a case study over the Sierra Nevada mountains. I want to show you a little bit of this geography. So this is the starting point for this work, which actually started with a bachelor's thesis at MIT by Catherine Materna. And what she did, she actually looked at outliers motivated by the fact that she couldn't understand why there are certain outliers at certain times and why they're asymmetric. If you're looking at GPS stations at this mountain range in the Sierra Nevada, then you can do a side-by-side comparison and analysis trying to understand why these outliers are there. And what she did was she looked at data from topography, weather, MODIS, and other data sources. And if you're looking at the map on the left, you see the skewness of these GPS stations near the mountain range, where you would typically expect lee waves to form. And then in the middle, you see time series with certain outliers, with certain asymmetric error patterns. And on the right, an excerpt from her work showing how does the typical wind direction look like when you have non-outlier days versus outlier days. And when I looked at this, my background is in computer science. I thought this is highly interesting. Let's try and scale this. So this is what this work is about, is basically take this idea and scale it and see, can we do it on larger regions, see if this leads somewhere. And this is the experimental setup for data fusion. So if you're looking, how can we fuse information from images with information from time series? For a moment, take a look at where the GPS stations are located. So they're located on the ground, and then you would look at certain GPS satellites. So you have line of sight propagation of GPS signals. However, if you have water vapor in the atmosphere and turbulence, you can expect that the signal is being delayed. And I'm showing you here two cases, one where the tropospheric component is 0 and the other where the delta tropospheric component is not 0. And you look at these time series, and then what we did, we created a metric that is essentially an outlier score, which is computed by a whole pipeline that I'm going to show you in a couple of minutes. But you can see that there's a pretty good correlation when one of these stations is in an area which has these Lee wave patterns that you can see from the satellite. So what we did is, for the imagery, we created the neural network that tries to identify these patterns, so you can see the area where these Lee waves form. And then on the GPS side, we have a pipeline that is trying to compute these outlier scores and then fuse these two together to say, well, we have a location here or an area where likely we have Lee waves. So let me walk you through this. So we do two things. Number one is MODIS. Here we built a convolutional neural network to detect Lee waves in the image. And to do that, we're tiling the image into 64 by 64 tiles. And each tile can be classified into yes, there's a Lee wave, or no, there's no Lee wave. So then we train a neural network with known instances of Lee waves. For that, we actually built an own Python GUI, which presents a user with tiles from images and just asks, please label these images, whether you see a Lee wave or not. And then later, we also use these classifications to perturb tiles. So potentially, if you want to rotate or scale tiles with Lee waves, that can be helpful later in the detection to detect more complex patterns. Okay, so this is MODIS, and for GPS, we do the outlier detection, and we fuse both data sources. So here's the overall pipeline that we are experimenting in this work. The upper pipeline is the convolutional neural network. The lower pipeline is the GPS outlier scoring. And I want to show you how this neural network works. So in the convolutional neural networks, you have different types of layers that are applied on MODIS imagery. And you can see we're starting with these 64 by 64 tiles, but then we apply the convolution, and then there's two types of layers, convolution and max pooling. And then in the end, there's two fully connected layers which actually lead to the yes-no classification. And for those of you who don't know much about neural networks, I want to take the time to educate a little bit what's inside this box. So technically, if you drill this down, this high-level image, you end up with different arrays that are interconnected and that are multiplied with different weights and different configurations. So I just want to take the time a little bit to educate those of you who don't know what the principle is, which is underlying in this network. Since this is the first session, you're going to hear a lot about convolutional neural networks today. So look at this toy example, with just two layers. So you start with a convolution matrix, and then you have your input image. For a moment, assume you have grayscale pixel values. And then you multiply element-wise the numbers in this convolution matrix with the values in your image, and then you sum them all up, and then you end up with a convolved image. So the sum of the multiplied values in this red rectangle becomes one number in the convolved image, which then has overall lower dimensions than the original image. Then on that, you would add a bias and apply a sigmoid function, which essentially thresholds all the values and creates another array where you have values that are between 0 and 1. And then you would select pieces of this array and do the maximum on those particular partitions, which is called max pooling. So then you end up with a maximum in another array, and these arrays are called feature maps. And now if you were to keep this number of layers, what you would do is you would connect these to this final layer, which has 2 neurons in our case. And then you have weights. In our case, it's a weight matrix. So you can multiply the weights in that weight matrix with the numbers in the respective feature map, include a bias, and then the neuron creates a value that is between 0 and 1, which you interpret as yes. So the yes neuron would be closer to 1, and the no neuron would be closer to 0 if you were to have a clear-cut classification. So on the bottom right, I show you what you can do to add more layers. So typically one layer or one convolution, one max pooling layer might not be enough. So what people typically do is they add more of those layers on top, which adds more abstraction levels to your problem. So you have more abstract feature maps as you add those layers. And notice that everything is linear. So you're actually multiplying and adding, which means you're introducing linear separations for your different kinds of features. And if the linear separation that you currently have isn't good enough, then you keep adding more layers. And that's why these networks are called deep neural networks, because this can be very deep. So in our case, this is what we did. So let me show you some preliminary results. This is from the training phase. And these dots represent center tiles that were selected to train the network. Note that we don't have to click on all the tiles that are Lie waves, because at some point the network learns what Lie waves are, and then you can apply that information to make actual detections. And here's an example of how the network would classify results. So you take an image, and then the network tells you here are all the tiles where there are Lie waves and where there are no Lie waves. And the ones with Lie waves are highlighted in red. And regarding the metrics, I want to show you that we try this on a pretty significant number of tiles. So in total, we have 300,000 tiles. And then the training set was 250,000. The other 50,000 were used for validation and the actual testing. So the training validation of 30,000 is meant to make sure that we're actually we actually trained the network on the right training set. And then the real result is the one on the 20,000 tiles, where we know where the Lie waves are and where they are not. And then we're sampling 20,000 tiles, and it turns out that we can find Lie waves with 96% correctly classified accuracy. So now let me switch to the GPS and show you that now we know where the Lie waves are in the image. Now we need to see where they are in the time series. And here are 2 examples. The upper example shows you time series from GPS where there are Lie waves. So you can see it's more distorted in a way than the lower example. And this can be quantified. So this is quantified by this pipeline that I don't have time to talk about in the image you've seen before. But at this point, just interpret the outlier score as a value between 0, which is blue, and 5, which is red. And then look at the GPS stations in California. So see where you're trying to find the red ones. And on the right side, we superimposed information from GPS, the modus detection, which are all these tiles, and a relief map. And it turns out these red dots appear where you see the mountain range where you would typically have the Lie waves. Okay, so time is up. I want to point you to our source code, which will be soon available online. So we have code under the MIT license. We have created a package, Scikit Data Access, that allows you to pull modus imagery with just 5 lines of Python. We have Scikit Discovery, which will include the neural network detection techniques that you've seen here. And for the science case studies, that's a repository of Jupyter notebooks where you can use all of our code to reproduce the results or maybe change parameters and play with them, or use all these notebooks for teaching in your own class. So thank you very much, and I'll be here around to take more questions if you have any. Thank you.
Thank you very much. We have time for one short question.
When you say you did data fusion with the outputs of those three models, is that just y'all overlaid them and analyzed them yourselves, or did you have a third model that interpreted the two outputs?
So right now, we interpreted the outputs. We created graphs and plots. We actually have a paper that's now being finished for submission. We don't have a third model that integrates these two yet, but I think we can get there. And we can send you a draft of the paper if you want to read it.
Thank you very much. Our next speaker is not one, but Alan Lee. We had to change the program, which isn't reflected in the online program. And he will speak on NEMO-NET, the Neural Multimodal Observation and Training Network for Global Coral Reef Assessment. And could you just start?
Yeah, I think it has to go to the first slide. Sorry for the music. I didn't realize it was actually going to turn on. But it's supposed to be soothing. That's the idea. So yes, I am Alan Lee. I'm very excited to talk to you here today about NEMO-NET. That's short for the Neural Multimodal Observation and Training Network for Global Coral Reef Assessment. So our team and I, we're mostly based out of NASA Ames over in Silicon Valley. Personally, I work at LAS, the Laboratory for Advanced Sensing, over at NASA Ames as well. And finally, this work would not have been possible without ESTO, Earth Science Technology Office, under the AIST grant of 2016. Okay, guess I'll have to click. All right, so I'm pretty sure all of you know what coral reefs are, but I just want to highlight exactly why they're important to us. So actually here it shows a map of all the coral reefs, most of them located out throughout the world, mostly centered around the tropics. And they actually provide 15% of the oxygen that we currently breathe. So you can imagine if these ecosystems collapsed, what kind of effect they would have on us humans. In addition to that, they represent tremendous value to the communities they support. Not least of which some of the things I've listed here, shoreline protection against tsunamis and other waves, economic value arising from tourism. They represent some of the highest biodiversity known to man on the planet. And even now we are discovering more and increasing medical applications related to the various types of life and biodiversities that we see in those ecosystems. As you may well know, in the previous few years, they have really come under tremendous pressure, not least of which comes from climate change and warming waters, but also things such as ocean acidification, pollution runoff, and a whole host of other human-related factors. And we are really seeing the die-off in the past few years of up to 25% of global coral reefs. So what I'm stressing is we are really in an unprecedented time that we are witnessing the decimation of these ecosystems at a large enough scale visible from space. This particular image is taken at American Samoa, and you can see the bleaching events, which is dying of coral reefs just over the past few years. So to really try to stop this from happening and trying to solve the problem, we really need to understand the problem first. So to understand the problem, we really need to know the extent of the damage and how fast it's progressing. This is where remote sensing comes in. So NASA and other agencies have a whole host of spaceborne and airborne assets that we use for imaging the Earth and oceans alike. However, as you can see on the right-hand video, that a lot of the airborne and satellite data that we collect are distorted because of these surface waves, otherwise known as refraction. And in essence, what we do is, right now, is we take a mean of the image, and what we get as a result is a blurred sort of image at the end. It doesn't help that as we move higher in altitude, our resolution naturally decreases, so from the left to the right until we get to Landsat where everything is just a blob. It's very difficult to do science at those resolutions, especially since coral reefs expand and really change at the centimeter scale. What we've done at NASA LAS is we produced fluid cam and fluid lensing to actually remove the surface distortions to give you a sub-centimeter view of the coral reefs underneath. So this is actually, I'm just going to show a bit of this video here. It's part of our campaign to American Samoa in 2016, where we imaged the coral reefs there using fluid cam and fluid lensing. So this is taken from our UAV, and it'll zoom in on the coral in a moment here. So this is the coral with the surface distortions and the sunlight even glinting off of the surface. So if you remove the surface distortions, this is detailed in a paper, but you can see that we are getting really sub-centimeter resolution and the bathymetry map of the corals as well. So this is the highest resolution available data taken from a source above the water surface and not with underwater vehicles in AUVs. So what is NEMO-NET's goals? So our goal is to actually create a fused global data set of global coral reefs using the data we collect, airborne and satellite data sets. So you can imagine, this is all well and good that we have these high resolution maps, but we can't exactly fly UAVs everywhere over all the world's coral reefs. So we do need to depend upon higher altitude assets to extend our spatial extent. We are in the process of developing coral-specific remote sensing deep learning networks, specifically convolutional neural networks, to quantify coral reef percentage and cover, morphology breakdown, and habitats. We're going to assess the present and past dynamics of global coral reef systems through transferred and adversarial learning methods. We're actually developing an app for our user base to use on active learning methods, using active learning methods. And finally, we are going to deploy NEMO-NET as a NASA Next, which is NASA Earth Exchange, and GIS open source product for the community to use. Oh, whoops. Can I go back a slide? So this is actually a breakdown of what NEMO-NET essentially looks like in its constituent parts. We have raw data coming in from UAV, airborne, and satellite data, feeding into a GIS platform, which we do all the data processing, preparation, and georectification. The heavy lifting is done through Python, which we're building through Keras and TensorFlow GPU accelerated modules. Here is where the adversarial learning, CNN architecture, transfer learning, and such is being implemented. This feeds into the active learning platform, which in cases where it's ambiguous as to what the data is, we hope the community and scientific experts will help us classify the corals, and this feeds back into the GIS platform, and eventually we get a better product. This eventually will also be rolled out. It's currently being implemented actually on our LAS Leica cluster, our own GPU cluster, and eventually on NASA Next and the Pleiades supercomputing cluster. So before I go on, this is kind of the schedule that we were at. This is a 2-year attempt on our project, and we are currently here on month 3. So we are really currently still at the inception of our project, but hopefully I can share some of our preliminary results with you. So this is some of the data sets that we've managed to collocate and put together, and more are actually incoming. But in addition to our data sets, the underwater AUV data sets from our partners and us, our MIDAR and FluidCam data sets from UAVs, we have mostly USGS data. This is mostly over American territories, US territories, Worldview 2, QuickBird, some airborne data, as well as NASA data coming from the Coral project, which is headed by NASA JPL, imaging the coral at 224 hyperspectral bands at a 7-meter resolution. Of course, there's also Landsat, which is at a much lower resolution, but goes back decades. I'm glad the previous speaker went over CNNs, because I have only this slide kind of explaining what CNNs are, but hopefully you get an idea from the previous presentation exactly what they do. The first 2 methods, maximum posterior estimation, SVM, kind of the bread and butter, naive Bayes and the support vector machines that classically has been used in this field, are some of the methods we tried first, and then we are comparing them with our currently our newer methods, CNN. It's an AlexNet-like structure, and VGG16 FCN, which stands for the fully connected network structure. So the first structure is very similar to a previous presentation, where we're actually trying to predict the middle pixel from an image patch that we put in. So you go through the various convolution layers, the kernels, and the max pooling layers to come up with the classes at the end. The second method is the fully connected network actually goes through an encoder and decoder portion of the network. So the encoder portion works the same way as the AlexNet, but in the decoder portion, we're basically upsampling and trying to reproduce some of the feature maps as we go up in scale, and eventually actually we come up with a segmentation map at the end of the day, and not classifying any particular pixel. This is some of the preliminary results we have on one particular transect of something that was imaged with our UAV and FluidCam. So you can see map estimation, SVM, the classical methods, they do all right, up to 90% and 86%. But the moment that you go to a neural network, and the neural network is actually trained upon about 1% of the total data, with validation and test sets, of course, you're hitting 92 to 94%. Interesting to note that the fully connected network is much less noisier, actually, than the other methods, but shows a slightly lower accuracy than AlexNet. Again, that's all well and good, but we've really only predicted upon the high-resolution data sets that we've currently collected with our UAV. So how are we going to transfer this to other data sets captured by satellites and airborne data? We actually developed a method, PCA SVM, not detailed here, which does domain transfer. But what we are hopefully trying to do is extend this to a CNN sort of method, in which we have adversarial learning. We try to generate a high-resolution image and have basically the CNN play against itself, trying to determine what is real and what is not. And in that case, hopefully we'll develop a better network that eventually comes up with a product, goes through our CNN training, CNN classification. We downsample it to the resolution of native data set and provide an output. And this is sort of an early beta version in the video that you see of our app. We have a more advanced version here on our iPad, if anybody wants to try later. Which we visualize the coral and let the user classify using a stylus on the iPad itself. And yes, there's more to come. Hopefully we'll be rolling out our active learning app for the scientists and user base alike by June or mid-2018. And we have some cool ideas. We would love your feedback on if you like it, what works and what doesn't. We have a storyboard. You move around the map in the world to classify coral. Very, very fancy stuff. And that concludes my presentation. We have posters, NASA Hyperwall talk tomorrow in the morning, and some material more on the interactive app side of things on Wednesday. So please stop by and help us classify some coral. Thank you.
Thank you very much. We have time for questions. Questions?
You said you were using the BGG and Alex type maps,
Yeah.
but you were also using like an autoencoder or like an encoder or decoder type network. So I was confused if you were saying that you were only doing the segmentation or you were also doing some classification with the maps you showed for classification maps.
Yeah, so actually we mostly want to try to do segmentation because the pixels are very dense in remote sensing. You really want to classify it on a pixel by pixel basis. And so you can combine AlexNet VGG16 with whatever an autoencoder, decoder network. So currently we've only experimented with AlexNet and VGG16 in that format, but we're hoping to go deeper, such as ResNet, and see how that stacks up to produce segmentation maps. So we segmented and labeled. Yeah.
Sorry, we want to stick to the schedule. Oh, thank you very much. But you're welcome to follow up. Our next speaker will be Paul Johnson to speak about machine learning on fault friction. Oh, so we have to change.
I'm covering for Captain. I'm in his team.
Okay. Briefly introduce yourself and have 30 minutes.
Hello, my name is Bertrand Wadeduc. I will be doing Paul Johnson's talk. So I'm going to talk about a method we developed to analyze large amounts of seismic data in order to estimate the physical state of faults. In particular, will be... Sorry. So I will be presenting a method about analyzing large amounts of seismic data in order to estimate the physical state of faults. In particular, we'll be interested in the frictional state of faults. So this work was done at the Los Alamos National Laboratory in collaboration with people from the University of Cambridge and people from the Pennsylvania State University. So in the first part, I'll give an overview of our method. So mostly this talk will address the data analytics part of the session, not so much the deep learning part. So I'll show how we're able to compress and extract physical information from seismic data and then feed it to ensembles of decision trees. I'll show that doing so we uncover signals in the data, seismic data coming from a classic experiment, signals that were thought to be noise, and then give us at all times the frictional state of this fault. So why do we care so much about the frictional state of a fault? It's because it's considered to be the most important physical bulk characteristic of faults. In particular, it's the friction that prevents, for instance, earthquakes. So when the tectonic forcing overcomes the friction, an earthquake happens. So that's why we're so interested in the friction. I'll show also that this signal we uncovered in this classical experiment, so those are all laboratory results. I'll show that this signal we uncover also enables an accurate forecast of the laboratory earthquake events. And finally, I'll give an overview of this signal we found. So first, I'll talk a bit about this classic experiment. So it's been studied for quite a few years. It's called the double shearing apparatus. It's composed of 3 steel blocks. the two outer blocks provide the normal stress that confines the fault. The central blocks shears to the fault, and it does so at a constant velocity. The force that's applied to the central block drops sharply when a laboratory event and laboratory earthquake happens. So here in red you can see this force that's applied to the central steel block. And those sharp drops over time, this data is over time, those sharp drops correspond to laboratory events. At the same time as we record this force that's applied to the central block, the seismic data that's emitted by the fault is also recorded. So here in the bottom left in black over time is the seismic data in arbitrary units emitted by the fault. So for this first result I'll show, we focused on a chunk of data where the laboratory fault is failing recurrently, but aperiodically. So it's an interesting behavior that's similar to Earth. We'll further restrict our data into training and testing. So for the training phase, our machine learning models will have access to both the seismic data and the shear stress data, which is equivalent to the friction data, this friction that's so important. And it will try to infer a model, try to find a link between the two. And the testing phase, our model will only have access to the acoustic data. So our inputs for this exercise are the dynamic strain, which is here in the lower plot. And it's the same as the seismic data. And we'll extract features from this. So the way we do it, have a time window that parses the acoustic data. And so we restrict the information the model has access to a small piece of acoustic data to force the model to try to uncover the current physical state, if there is such information in the seismic data about the fault. So we have this sliding window. It computes several statistical features of the seismic data, and we then label it with the stress, so the bulk behavior of the fault. So this seismic data, it comes from microscopic interactions inside the fault between the grains and the steel blocks, whereas the stress, it's a bulk behavior. So what we're trying to uncover is there something in the microscopic behavior that we can remotely sense that tells us about the bulk physical behavior of the fault. So our database, it's those features, those statistical features of the seismic data. Our label, it's the stress. And so in the training phase, we feed it to ensembles of decision trees, random forests, or gradient boosted trees. And then we test our model. And so first I'll show, as regards the friction or the shear stress, it's a proportional, so equivalent. So we have this time window that takes a small slice of the seismic data. This slice is much smaller than the seismic cycle. So we restrict the information the machine learning model has to make predictions from to a tiny portion of seismic data, a portion of seismic data that's much smaller than the scale of a laboratory failure cycle. So it's the testing data. This ensemble of decision trees has only access to the acoustic data, and it makes those predictions in blue over time. And the real data, it's in red, and it's extremely accurate. So what it shows is that, at least in the laboratory, at all times in the seismic data, there is a fingerprint of the bulk behavior of the fault. So this experiment, it's a classic one. It has been studied for many years, if not decades, and that's new. So using the same method now, I'll show that at least in the laboratory, there is also in the seismic data fingerprint about how close this laboratory fault is to failure. So again, the same procedure. We have a moving time window that passes the seismic data. It extracts a long list of statistical features. That's our input. And it is then labeled, this time not with the stress or the friction, but the time to failure. So at one line of our machine learning database, it's a small portion of time that gives us instantaneous statistical features of the seismic data. And it's labeled with the current time remaining before the next failure event, the next laboratory earthquake. And again, it works really well. So this again tells us that at all times, whether we are at the beginning of the earthquake cycle, the middle, or right before it happens, there is a fingerprint in the seismic data of how close the laboratory fault is to failing, is to a laboratory earthquake. So this piece of data I'm showing the results on, it's quite periodic, but there are outliers, and they're picked very well as well. Now I'll just show a bit more details about this signal we're finding. So as I said, it's a classic experiment. It's been studied for a long while. It was already known that not long before a big failure event, so a laboratory earthquake, oftentimes there are impulsive and large emissions in the seismic data that are precursory. So oftentimes preceding a failure, there are impulsive events. So that was already known. What wasn't known is this fingerprint we find in the seismic data that tells us at all times what the friction is on the fault. And so it's a very unremarkable looking signal. It looks like noise and was discarded as being noise for many years, or so far. And so this signal also, it doesn't look like much. A small piece of it at any time during the strike cycle, although it comes from microscopic interactions, it tells us very precisely what the bulk behavior is of this laboratory fault. So I'll conclude. We're able to build a machine learning model that shows that there is a link between the microscopic behavior and the bulk behavior. We found it a bit by chance. We were mostly interested in those precursory events when we started this machine learning project, and we stumbled upon this signal using an unbiased method that machine learning methods are. And it shows that at all times there is a fingerprint of the state of the fault embedded in the seismic data. So from the start, we forced the machine learning models to have only access to instantaneous information, and that's why it's been able to capture the physical state of the fault using this new signal we uncover that was previously thought to be noise. So we started expanding this method, trying this method in a few different experimental conditions. So far mostly on the same experimental apparatus, so in different experimental conditions with different materials. At least for this laboratory experiment, there is always in the seismic data information on the physical state, the bulk behavior of the fault. So this method we developed, it extracts information out of a very large amount of seismic data, terabytes, and turns it into a small machine learning databases. It's somewhat inexpensive to run. It's easy to implement. The results you saw were done mostly with just a single desktop. Many systems remain to be explored. We used our method also on classic almost simulations, so model simple simulations, and we found this same fingerprint for the bulk state of the fault from microscopic interactions. Now we're working on applying our method to different experimental apparatus, and of course real faults. Thank you.
Thank you very much. We will have to move on to our next talk. Thank you. We don't have time for questions right now. And our next speaker will be Manil Maskey to speak on large-scale labeled datasets to fuel earth science deep learning applications. Hey, hello. It's on the Mac computer.
Oh, it's in the Mac, yeah. Second one. Yep. To flip it. Hi, I'm Manil Maskey from National Marshall's Data Science and Informatics group. I lead the data science part of the group, and Rahul is the overall lead for the group. Last few AGUs, I've been talking about applications of deep learning for earth science. So this year, I thought I would give you some of the challenges, mainly creating this large-scale training data set for earth science and challenges within that. So just a little bit of background. We started our deep learning journey about 4 years ago with the funding from NASA's ESTO AIST project, and we have taken quite a bit far using that as our initial means of doing deep learning. So use this. So deep learning is nothing new, right? It's a subfield of machine learning. These are algorithms based on how our brain functions. And the key thing here is that it scales with amount of data you have, and mainly the training data, right? And the scientists come to love it because in past, people have used domain expertise to create features. But with deep learning, you don't have to have a domain expert creating features. It actually learns the feature from the data itself. And I'll show you why it is suitable for earth science applications. We have a lot of data in earth science, right? We have a lot of missions that are coming up, large-scale missions coming up. But why is it still hard for using deep learning for earth science? So in the industry, there's a lot of success using deep learning, right? Each of these industry giants have one thing in common. They have lots of data. So they have used that to create all kinds of services. Almost all the services you see from the industry uses some form of deep learning. In terms of science, medical science has taken it furthest than any other area because of all the diagnosis and label data that they have for quite a while. So what is needed for deep learning, right? So one thing in common in all these applications, you saw there's a lot of data. So it used to be data was the new oil for big data, right? So in machine learning, it's the training data that's the new oil. So manually creating these labeled data set is becoming a bottleneck. We saw a couple of examples where users were being asked to create training set, right? So that scales up to a certain point, but beyond that, what do we do? So it's becoming a barrier in deep learning. So here are a few of the popular network that exists, and look at their training size. So the VGGNet was talked about earlier. It uses to classify images, right? It has 1,000 classes as output. For deep video, which uses to video classification has 47 classes. And the GNMT, which does the language translation from English to French, look at all the labeled data size, 1.2 million images, 1.1 million, and 6 million, right? There's a lot of training data already there. So I mentioned we started our deep learning about 4 years ago. These are some of the applications that we have applied for, mainly for detection and classification. And one of the applications will be talked about in later presentations here. And recently, we've been collaborating with Carnegie Mellon University in terms of using deep learning for entity relations extraction from literature as well. So with all those applications, you can see the training data size, initial training data size we have created. It's not as quite big as some of those networks that you saw early, but our problem is not that complicated. We're not trying to classify everything in the world you see, right? It's for just look at the example of the hurricane intensity, which will be talked about later. It has about 8 classes as output. So initially we had 49,000 images to classify against. So in terms of collecting these training data sets, our methodology has been, 2 of them has been fairly manual intensive, like suggested earlier, where you actually ask the user to label whether it is, it has some phenomena or not. Some of the other applications, we're able to combine existing data sets, imagery versus reports, or imagery versus other secondary text data to fuse the data together to create some training data sets. So what are the strategies that exist in terms of creating these large-scale labeled data sets? So here are a few that we have used and some that we're trying to use. I'll go into a little bit of detail on each one of them. So data augmentation, it's fairly simple. It's mainly used on computer vision tasks like the ones we saw earlier, where you transform the image using some image transformation techniques, right? One of them is mirroring. It may apply or may not apply to depending upon the applications. The other one is random cropping. You crop the images based on randomly crop the images and use that as a training set. There's color shifting approaches. There's also PCA-based approach where you take the PCA across the entire training set and use the eigenvalues to scale the RGB values. And the idea here is that as long as you fundamentally don't change what you're trying to learn from, your training size will actually help the accuracy. So transfer learning is probably the simplest of all, where you're trying to use existing model to train something for your particular need. So the idea is instead of training the network from scratch, you actually use the already trained model on your task, right? So, but there are also ways to fine-tune the learned model. For example, you have feature extraction. If you're just trying to use the feature extraction from a learned model, all you have to do is change the outermost layer, classification layer, so that instead of classifying to 1,000 classes, you classify to just 2 classes. Second approach is just keeping the architecture the same, but changing the weights of your network. And that works in some cases. I'll show you when to use some of these. And there are also strategies like you keep part of the network same and just change the weights for the rest of the network. So here's an example of when to use a pre-trained model. Is quadrant where if you have a similar data that the model was trained against versus what is the size of your training data set, right? So ideally you want to be in that top right corner where you have lots of, the data is similar to your trained model, plus you have lots of data. But ideally that's not the case, right? If you already have that, you probably don't need to train a model. So if you have a lot of training data and your data is not similar to your trained model, you probably should start from scratch because you have a lot of training data already. And the lower two cases is where your data is similar and training data is small. You just change the outermost layer. Or if you have less similar data and few training data sets, you probably want to fine-tune the layers, initial layers, and train the model again. There's also something called permutation invariance. This applies when there's no spatial relationship within your data, right? So this will not really apply for a convolution neural network where it's trying to preserve a spatial relationship. So the idea here is that if you have ordered vector set of information and the ordering of the values doesn't matter, then you can apply basically this approach. An example would be, let's say you have a county level information for remote sensing data, but you also have pixel level classification. Then you can combine those two into where the ordering of the pixel doesn't really matter for the county level classification. There's a new paradigm called data programming, where you can actually use programmatic approaches to create training data sets. So in this case, you have a lot of unlabeled data sets, but you have some domain expertise who can create labeling functions, which basically turns into weak supervision. And they can choose a discriminative model. I can go into a little bit of detail on this. So a weak supervision will be some sort of domain rules or heuristics, right? If there is a ground truth information that you have, but it doesn't exactly fit your need, but you can also use that as a domain weak expertise, weak supervision. And you can combine this set of weak classifiers into something called boosting to come up with a very stronger classifiers. And obviously there is crowdsourcing approaches where non-experts can also make annotations. So these are all kinds of weak supervision. So here's an example of what we've gone through, information extraction from earth science literature, right? So it's a lot of unstructured text. You want to come up with things like data set usage, what is the hypothesis in the earth science literature. So there is no labeled training data set for this, right? But there are various ontologies, vocabularies, glossaries that already exist. You can also come up with some custom heuristics, right? There's also rule of thumbs, regular expressions, and you can also use negative label generation. So how can you combine these? Okay, I need to move on faster. So here's an example of studying dust events. So in a sample text in the literature could be pronounced changes in aerosol optical parameters derived from AeroNet have been observed during dust storms. So you see the word dust, you see the word aerosol, right? So one labeling function could be, hey, if there's a mention of phenomena and a property, please look at the domain knowledge. So in this could be domain knowledge could be a sweet ontology. If it exists, there's a label, you can label that as a true statement, right? So you can extract information like that. The second is a domain heuristics, where two words are separated by derived, word derived. That could be another true labeled data set. So if you want to use data programming framework, there is a nice framework developed by Stanford, which allows you to do the same things that I mentioned earlier, called SNORKEL. It has a very nice interface, and it also trains with a noise-aware discriminative model. So in our approaches, these are the strategies that we use. So we haven't used the data programming yet, but we probably will in near future in terms of entity extraction. So my idea is to pitch this thing where if all of these data sets have so much value in deep learning, why can it not be part of a regular data set publication, just like we publish all the science data sets, like in NASA CMR, right? We have a lot of scientific data already available there. Amazon already publishes data sets like these for machine learning. We should be able to publish these training data set as part of our catalog as well. These are my takeaways. Basically, we need labeled data sets to better our performances for deep learning and machine learning. and challenge has been to create these training data sets. Algorithms are not the problem because you can always fine tune to get the accuracy high, but we need labeled training data sets. That's all I have.
Thank you.
I ran out.
Thank you very much. Our next speaker is Jeffrey Miller to speak on using deep learning for tropical cyclone intensity estimation.
Thank you. So hello, my name is Jeffrey Miller, I also go by JJ, and I wanted to talk to you about our project we've been working on called Using Deep Learning for Tropical Cyclone Intensity Estimation. I'd like to acknowledge my co-authors, Maskey, who just finished speaking, and Todd Berendez. So this presentation is going to focus on our preliminary work. Specifically, I'm going to talk about our motivations, the current techniques that that are used by scientists in the atmospheric science field, data we use to train our network, methodologies. I'll also talk about some of our results, the potential applications, and the steps we plan to take moving on in the future. So currently, the most accurate means for getting tropical cyclone intensity is through aircraft reconnaissance observations. However, these measurements are not always available due to the fact that the aircraft need to land and refuel. So whenever recon data is not available, satellite-based methods are used. These methods tend to be objective, or excuse me, they tend to be subjective. They require domain experts, and they can sometimes result in different intensity estimations for the same storm. The National Hurricane Center even estimates that a 10 to 20% uncertainty in post-analysis when only satellite-based methods are available. So we wanted to know if deep learning could be used to remove subjectivity from hurricane intensity estimations while maintaining high levels of performance that is achieved with current techniques. So the Dvorak technique is by far the most popular technique when it comes to intensity estimation, and it estimates intensity by analyzing patterns in the storm's shape and then applying a set of rules. It can be subjective since the user must decide which pattern the storm has from a predefined list, and this can lead to two different intensity estimations for the same storm. However, the Dvorak technique has stood the test of time and it still uses the primary intensity forecasting tool in many tropical cyclone forecasting centers worldwide when recon data is not available. The objective Dvorak technique was created in 1998 to try to reduce the amount of subjectivity by using computer-based algorithms to recognize the cloud patterns, but it still relies on an expert to identify the center of the storm. And the advanced Dvorak technique was created in 2007 in an attempt to further remove subjectivity by introducing regression equations and an objective storm center determination scheme. So comparing current methods to deep learning, the current methods are often subjective and they don't generalize very well. Also, they can be inconsistent and they have a tendency to be inconsistent, and they're dependent on users being an expert in the domain since there are many regional nuances and adjustments that need to be taken into account. With deep learning, those methods are usually objective and they tend to generalize very well, and they also don't require any user expertise. The one downside to using deep learning is you need a large amount of training data, but luckily enough, the Naval Research Laboratory has been collecting a bunch of tropical cyclone images from all the way back to 1997. So the data we used in this study is from the U.S. Naval Research Laboratory. We used images from 2000 to 2016, which are typically available in a 30-minute interval. We used images from the Pacific and the Atlantic basins, and these come from multiple sources such as GOES, Himawari, and MTSat. There's also a few polar orbiting satellites thrown in there too. So in total, we had around 45,000 images, give or take a couple hundred. So in order to label the images, we needed to find a data set that had the intensity of the storms. So the best way to do that is through HERDAT or HERDAT2. This is a post-storm analysis that is that provides an analysis of intensity, central pressure, location, and size, and it's available in 6-hour intervals. But the 6-hour intervals is not enough, wouldn't give us enough training data to train the network properly. So we needed a specially subsetted portion of that HERDAT2 data set. This was restricted to time periods where recon data was available, and this gave us 1-hour intervals, which greatly increased the number of images that we could label if we had rather than using the HERDAT reanalysis alone. So for the methodology, we decided to sort the images based on maximum sustained wind speed with an interval of 5 knots, and this gave us 18 different classes. So when labeling the images, we decided to use the image that was taken closest to the reference intensity time. So if there was an image taken at 8:45 and there was an image taken at 9:10, we would use the image from 9:10 for the reference time of 9 o'clock. And some of the images had missing data. This was only really the case for the polar orbiting satellites since they have swath images. But if that was the case, we decided to remove any images that had 20% of the pixels were black. So, and we also split the data into train, test, and validation sets. And we also augmented the images before training using rotation and zooming to artificially increase the training images. So the network architecture we used was the CAFE reference network, which is very similar to AlexNet. We utilized transfer learning with the base network being trained on ImageNet. So we froze the first 2 convolutional layers. We didn't train those at all. And then the following 3 convolutional layers, we trained those at half of the learning rate. We also removed the fully connected layers and replaced those with newly initialized layers and then trained those normally. We used the deep learning library called Keras through the NVIDIA Digits deep learning training system, and we trained the network on a NVIDIA Tesla P100 and achieved a validation accuracy of roughly 90% during training. So for our preliminary results, we achieved a top 1 accuracy of 86.4% and a top 2 accuracy of 93.06%. The evaluation metric for current techniques is root mean squared error, and our network achieved a root mean squared error of 10 knots. Our model is able to classify storms from both the Atlantic and the Pacific basins without having to utilize different networks. This is different from current techniques which utilize different algorithms for different techniques, or for different basins, excuse me. And so the top 2 for the North Atlantic are Pineros et al. With a root mean squared error of 14.7 knots and Ritchie et al. With a root mean squared error of 12.9 knots. For the North Pacific, the best technique is from Ritchie et al. With a root mean squared error of 14.3 knots. So our network outperforms the top techniques from both basins without the need for multiple networks or algorithms, all while remaining completely objective. So as I mentioned earlier, the Dvorak technique estimates intensity by analyzing patterns in the storm shape, mainly the outer bands of the storms themselves. So we wanted to see what features of the storm the network might be using to make its classifications. On the left side, we have an input image, and on the right side, we have 9 of the 96 activations from the first convolutional layer. And looking at the activations, it appears that the network is activating on the outer bands of the cyclone. A single filter can't tell you what the network is looking at, but in this case, many of the filters appear to be activating on the clouds within the outer bands of the storm. So this leads us to believe that the network is using these features along with others that are not immediately obvious to make the classifications. So some of the ongoing research that we've been working on, to align more with current techniques, we'd like to train the network where the storms are unique to the test and training set. So what we mean by this is throughout the lifetime of a storm, there's many different images, and we'd like to develop the training set to where a single storm is kept within the training or just the testing set. So we can hopefully that will remove any bias that the network picks up while it's training. We would also like to include data from different sources. So data like microwave imagery we think would also enhance the training because that is providing a better picture of the eyewall structure, which is often obscured in IR imagery. Another thing we'd like to do is We'd like to try out other techniques such as modality hallucination, which would allow us to train from 2 data sources during training and then only have to use one of those data sources during test time. And we'd also like to include other techniques use other techniques that include temporal information, such as a multidimensional LSTM network. So along with improving the network performance, we've been developing an intensity estimation service. This service will monitor the National Hurricane Center invest areas for tropical cyclone activity, and when the activity is identified, we will download the images from relevant data sources and predict that intensity. The predictions will then be stored in a database which can be retrieved through an API, and we plan to work with end users to develop a website that will display storm information along with intensity estimations and relevant overlays generated from the intensity estimation service. And all of this will utilize standard-based services. So here's a visual description of the intensity estimation service I was just telling you about. So starting from the left, we will monitor the NHC invest areas and process that information in the cloud. We'll then download the relevant data from the Earth Data Cloud storage and generate an intensity estimation, which is then stored in an S3 bucket that can be accessed or distributed to other applications such as the Hurricane Portal. The right side of the diagram is showing how we plan to train the network or train the model as new training data becomes available. So since HERDAT, the data that we use to label the images, that is updated annually after every hurricane season, and so we'd be able to use that to train the network in the cloud to improve its performance throughout the lifetime. So some of the main takeaways from my presentation. We've shown that deep learning can be used to remove subjectivity from tropical cyclone intensity estimation and even provide better results. We've achieved an accuracy of 86.4% with our initial network, and we believe that the performance should only increase with more training data. It seems that the network is using storm shape, which is similar to current techniques when extracting these features within the image. And we've been building a near real-time web service in the cloud to generate and distribute intensity estimations. I would like to thank Dan Cecil for his tropical cyclone intensity estimation guidance, and I'd also like to thank Darren Herndon for providing the special HERDAT data that we use to label the images. Thank you.
We have some time for questions.
Yes.
Do you expect latency time will be the requirement of the NASA lens program?
I'm sorry, I can't.
You are developing a near real-time services.
Correct.
Do you expect the latency time will meet the requirement of NASA lens program?
I'm not.
3 hours basically, that's the requirement of latency time. Because near real-time service. NASA lens program.
So I'm not as familiar with that portion of the project.
But what's the latency time you expect?
The latency time?
Latency time.
It shouldn't be very long at all. So once.
The initial approach is to use Goddard. Isolation would be different. And we're trying to do some tracking micro data sets with student banks, and based on that, we can improve that even more.
Is that it? Thank you. Oh,
Just one question. So, you said the RMSE was about 10 knots for your. Do you know what the RMSE would be for like the Goddard method?
It was above the ones that I mentioned, so I think depending on the technique they used, I think it was anywhere from 16 to 18. I'm not off the top of my head. I'm not positive though.
Thank you very much. Our next speaker is Ankur Mahesh to speak on assessing uncertainty in deep learning techniques that identify atmospheric rivers in climate simulations.
My name's Ankur. I'm an undergrad at Berkeley, and I'm very fortunate to be part of a team at Lawrence Berkeley Lab with Mayur, Karthik, Sue, Samira, Vincent, Dean, Prabhat, Berlin, and headed up by Travis and Bill Collins. We're interested in looking at the uncertainty of deep learning techniques for atmospheric rivers and other extreme weather events. Atmospheric rivers are extreme weather events that are Atmospheric rivers are extreme weather events that are long, narrow columns of moisture in the sky. When they make landfall, they can release as much precipitation as hurricanes, but if they don't make landfall, then states like California can face long, intense drought. They're a great case study for testing deep learning because there's no community-accepted standard for identifying atmospheric rivers. The current strategies are subjective, and they rely on arbitrary thresholds that most likely will change with global warming. That means that atmospheric rivers are ripe for a unique machine learning problem because there's uncertainty with the ground truth label data itself. To motivate why deep learning is the right approach as opposed to standard machine learning techniques that have been used for a few decades, we compared logistic regression, k-nearest neighbors, support vector machines to convolutional neural networks, which are the industry standard for deep learning for computer vision. And convolutional neural networks consistently performed best in terms of accuracy in identifying tropical cyclones, atmospheric rivers, and weather fronts. Another benefit of AR detection specifically is that atmospheric rivers, when classified by deep learning, don't require any form of an arbitrary threshold. Rather, the algorithm will learn the underlying patterns in the data to formulate where the rivers are. So the convolutional neural networks find the patterns in an image through two phases. The first is feature learning, where a filter slides or convolves over an image and it extracts features. And the second is classification. Now, in the classification phase, it maps the features that it learns to the likelihood that an image belongs to a class. Most of the compute time is spent in the feature learning phase, the first part, but most of the memory requirements are in the second part with classification. Transfer learning is one type of technique that deep learning and convolutional neural networks use in an effort to reduce the first part, to reduce the compute phase. So in transfer learning, you take a model that's trained to solve one problem and use it to solve a different one. The reasoning behind this is that neural networks are excellent generic feature extractors when they're trained with millions of images. So in transfer learning, the first step is you take the feature learning part of a neural network and train it on one data set. The second step is you remap those features that you learned to classify images in another data set. So in our example, you would take features learned by any data set, it can be even dogs or cats, and you use those features that it learned to reclassify it with atmospheric rivers or not atmospheric rivers. The key benefit of transfer learning is that you no longer have a requirement for a large label training data set. So to see how transfer learning stacks up with other forms of neural networks, we come to the first form of uncertainty. That's architecture uncertainty. So we tested several different neural network architectures, some with 1 layers, 2 layers, 3 layers, and then the most was 16 layers. The catch with including more layers is that you need more label training data. So state-of-the-art algorithms that classify things like dogs and cats have a huge advantage over climate scientists. People will take infinite pictures of their dogs. You can check a Snapchat. But there isn't nearly enough information for a satellite image. So a neural network is trained by minimizing a loss function. That simply is a function that characterizes or quantifies how well a neural network is doing. So the 16-layer architecture used transfer learning, and it had the highest accuracy at 92% and the most rapid convergence. The layers trained from scratch took 8 to 12 hours. Transfer learning took 20 minutes. So the uncertainty here is what type of architecture do we use? Where do we incorporate transfer learning? How many different layers do we incorporate? How do we optimize the function? And these are standard in deep learning as a whole. To understand how transfer learning works, we can walk through an example. So on the bottom left, there's an image of an atmospheric river that was correctly classified by the model. This model was trained on a data set with millions of ordinary images, like dogs, cats, benches, and stoves. Now, to see what the neural network is learning, we included a test. The first step of the test was to set part of the image to 0. So the black square is pixels that have been set to 0, and we record if the model classifies the image as an AR or not. Then we set another part of the image to 0, and another part, and so on and so forth. Each step, seeing if a part of the image was set to 0, what does the neural network classify? Eventually, with all these records, we made a heat map. Now, the heat map shows that when the bottom left portion of the image is set to 0, the model doesn't think the image is an atmospheric river. But if the top left or the top bottom right is set to 0, the model does think the image is an AR. And that is extremely promising, because what makes that image an AR is that long, narrow column of moisture at the bottom left of the image. So the conclusion is that even though the model was trained on things like dogs and cats, it learned generic features. And those generic features still make the image an atmospheric river. Now, up until now, we've been talking about a classification problem, which is the left column of the image there, where you take one picture and you have one label. But we also wanted to see if neural networks could tackle a harder problem, where you don't classify each picture, you classify each pixel in the picture, and that's called semantic segmentation. Now, semantic segmentation doesn't distinguish between multiple instances of the same class, but it does distinguish between the people, the road, and the cars that you can see on the right column. So the first step in an effort to explore the segmentation problem was to generate labels. We needed a labeled data set of things to explore. The two extreme weather events that we chose to tackle were atmospheric rivers and tropical cyclones. The way to generate atmospheric rivers is, unfortunately, to go back to subjective thresholds. So we isolated areas that were 1,500 kilometers long with 95th percentile integrated vapor transport. That's a measure of the horizontal transport of water in the air. The second type of extreme weather that we explored was a tropical cyclone. And for that, we used a toolkit for extreme climate analysis that again used thresholds to draw bounding boxes. This leads us to the second layer of uncertainty with deep learning in climate science, and that is uncertainty with labels. These labels themselves are uncertain. They're just atmospheric scientists' best guess, but we want to see if deep learning can be more concrete at getting us better forms of extreme weather events. To see how the segmentation model performed, there are a few examples of the left, which is the ground truth subjective labels, and the right, which is the model prediction. Now, in the top column, you can see that the ground truth and model predictions are very similar, showing that the neural network learned the general structure of an atmospheric river. The middle row of the figure is particularly interesting, because on the left, you have a somewhat messy identification of an atmospheric river. It's arbitrary based on thresholds. But the image to the right of it with the model prediction is far smoother, far cleaner, and far more physically sound. That means that model predictions are removing the reliance on arbitrary thresholds because the model sees thousands of sample training images, and it's taking the best of all the worlds in those training images. And finally, even though a tropical cyclone and atmospheric river often occur right next to each other, the model is able to distinguish where they are, is able to distinguish the separations between the two. Finally, we look at the last layer of uncertainty, and that is metric uncertainty. So if the whole point of a deep learning model is to be better than the labels with which it was trained, then the metric with which we use to analyze that model is particularly important. Now, the overall model's accuracy was 92%, so 92% of pixels were classified correctly by a segmentation deep learning model. But the ground truth labels were generated using much more information than the model was provided. The ground truth labels relied on thresholds in integrated vapor transport, geopotential height, wind velocity, and sea surface temperature. The model input was just given one field, integrated water vapor. But with a fraction of the input information, the model still learned 92% of the correct classifications. This is impressive and promising in deep learning for extreme event detection because it can identify patterns in less information and more effectively. But again, we want to investigate the uncertainty with the model, and that's where metric uncertainty comes in, the third and final level of uncertainty that we encountered. Now, in metric uncertainty, we want to investigate how to evaluate the model when the ground truth is imperfect. So for example, let's say the model found an atmospheric river that a threshold missed. In that case, the model will be penalized because it's less accurate, but in fact, it should be rewarded because it's proving to be better than the ground truth from which it came. So in the future, we want to investigate how to represent the three layers of uncertainty: architecture, label, and metric. Once we can investigate these three forms of uncertainty, we'll be sure in being able to analyze the output of deep learning in a more concrete fashion. Now, one strategy for tackling uncertainty is to use an ensemble-based extreme event detection. In an ensemble-based detection, our strategy is that we would train multiple neural networks, also called an ensemble of networks, on different labeling algorithms. Then we look at an image and we make a classification based on the results of each member on each neural network in the ensemble. That way, when each network votes on whether or not an image is a particular type of extreme, we're incorporating multiple different labeling algorithms into a neural network. Another way of tackling metric uncertainty is to come up with an expert hand-labeled data set. Now, this won't rely on subjective thresholds. This will be objective, gold standard ground truth. That way, we won't have to have a chicken and egg problem where the model is being trained on something that's imperfect and is actually leading to better results, as we saw in the previous slide. And the final tactic for neural networks is to use neural networks to detect other classes of extremes, such as weather fronts. Ultimately, I wanted to express a sincere amount of gratitude to the Department of Energy for supporting this work, as well as the Regional and Global Climate Modeling Program. Because deep learning can find information with a fraction of the input variables, it's an impressive and promising way forward for extreme event detection. Thank you.
We have time for questions. Cool.
Yes. You mentioned that the neural network seems to give you better results, more coherent, and so on, but how do you make that judgment? In other words, how do you make the judgment how is that judgment made? That the neural network, although it doesn't agree with your numerical criteria, the neural network is better. You know, AR identification or classification.
The way that judgment is made is through experts looking at and comparing the result of the ground truth labeling thresholds and the output of the model. That's an exact area of uncertainty that we want to make that judgment. That's metric uncertainty, which is a huge priority for us going forward. Another benefit of using deep learning is that it's relying on patterns, not arbitrary thresholds to begin with. Yeah.
Can you talk a little bit about false positives and how you avoid having an overly expressive model?
One way of tackling false positives is to ensure that is to use an expert gold standard labeling data set. So if we have a data set that is specifically hand drawn by experts, then we can explore how the model is doing with respect to false positives or type 2 error as well. Another tactic of false positives is to look specifically at each instance of a false positive, because it may be that the reason it's finding a false positive is that the ground truth threshold just missed it. The threshold changed with global warming, so we needed a new threshold that the ground truth doesn't know, but the neural network does.
We have time for one more question. If there's no more question, let's thank our speaker. And it's my honor to introduce our invited speaker for this session, Kwo-Sen to speak on simplify and accelerate earth science data preparation to systemize machine learning.
Thank you. I see. Okay, the mouse is gone. Oh, no, sorry, that's all right. Okay, so you have already seen the title for a few minutes. And it's work done by myself, Mike Riley, and Hamid also from Goddard mostly. And related to because this is a rather involved matter, so I'm in this 10, 15 minutes, I can only wave my hands. But more details are in these related presentation here at AGU. We have 2 more talks on Tuesday and Wednesday, and poster presentations on Wednesday and Thursday. And also there will be a live demo at the EarthCube booth on Tuesday, Wednesday, and as well as Thursday. So what has this got to do with this session? Because we are talking about recent advances in machine learning, and I'm going to talk about data preparation. Because deep learning is a subset of machine learning, and it's under, both of them are under the umbrella of artificial intelligence. And as you know, convolutional neural networks is a prime example, exemplar approach for deep learning. And I don't know about you, I'm kind of tired of it by now. Deep learning also, but deep learning, like many other AI techniques, also suffer from generalization. And I'm going to elaborate on that a little bit. It is very good for specific tasks through supervised training, as you have seen the many examples presented before me. And it's like image classification, pattern recognition, and facial recognition sort of things. But it does not make macro, what I call macro connections. It does make connections, within its confined domain, but it doesn't make macro connections, and therefore not inferences. For example, deep learning, a CNN trained for recognizing tropical cyclone will not immediately recognize extratropical cyclone or make a connection or a correlation, the relation between the two. So applying deep learning to specific efforts then establishes what I called isolated silo of excellences. So the next step, I believe, is to actually make connections between the silo of, among the silos of excellences. So I think that next step is the logical step is to mine, establish, and utilize, exploit connections among the different things, phenomena, or features that have been already recognized. This will require definitely big data, and otherwise it cannot be truly deep. So the question is then, how do we facilitate that, and with what infrastructure that will give us the best value, the cost effectiveness. So making connection, I'm proposing to make connections in earth science through what I call phenomenon mining. So like hurricane is a phenomenon, the atmospheric river is a phenomenon, but the phenomenon, the definition of phenomenon can be quite open-ended. So you can, specify a criteria that will be your phenomenon, all right? So basically, the phenomenon mining, what I mean is that by identifying and tracking phenomenon episodes in long-term data with expensive coverage, continental or bigger coverage. And these are natural features of the Earth climatic system. And it involves, most of the phenomenon involves distinctive and very specific processes. So this sort of mining will also aid in model diagnostics and establish targeted, and they will enable targeted data discovery. So for example, I'm studying AR, Alamos River, and I can use the phenomenon found, identified, and to find more detailed data in order to study certain episodes, be it MCS or Alamos River or extratropical cyclones and whatnot. Okay, and also another thing spoken of earlier is you could use these phenomenon to find more training data, because these are, once you have the spatial temporal coordinates, you know where that happens. Then you can find data, and those will be somewhat called already labeled or trained data that you could use for training your neural networks. And then the ultimate purpose is to enable the connection mining among these events, or the phenomenon, events of the phenomenon. So talking about big data, I cannot avoid to talk about the V's of big data challenges. It started with volume, velocity, and volume, variety, and the velocity. Basically, we need to scale both volume and the variety in order to achieve the desired velocity. But then later, veracity is added, which is appropriate for especially scientific endeavor. But all these need to be evaluated. So you may have multiple different approaches to do this, but eventually the value of the approach should be evaluated. So I'm focusing here on scaling variety. So parallelization is the obvious way to scale both volume and the variety. And I'm here not only the multi-threaded capabilities, parallelization, but also distributed parallelization. And even more so is the popularization of these massive parallelization capabilities, parallel capabilities. So that is to allow the scientist to leverage the massive parallelism without actually having the expertise for parallel programming. It's like, when we use our cell phone today, the smartphones are all multi-core, but we use it, we leverage the capability without knowing multi-core processing or programming. Therefore, for deep learning in earth science with big data, parallelization or popularization beyond the multi-core parallelization is needed. That's for the scientists' benefit. So now I'm speaking of a major pain point in all these endeavor. And most of the scientists, I think you are very well aware of the painful process of data preparation. And here, 3 studies pretty much quantified that pain. Okay, this is from one of the surveys. We spend 80% of the time in data preparation, according to this survey. And cleaning data and organizing data and collecting data sets are ranked among the least enjoyable. So we basically spend a lot of time not doing data analysis, but actually in doing, acting as data generators, right? So that's the unproductive part that we would like to address. Variety is really the culprit, and here I listed some of the variety issues, the data cleaning that in the business intelligence world that they have to do. And this is seriously hamper our productivity, and that's the value of our approach. Luckily, in earth science, we don't have to do as much data cleaning. A lot of that is being done for us. And, but we still have a lot of a variety to deal with, variety in data source. How is the data obtained, spaceborne or ground-based, in situ or remote sensing, active or passive, what viewing, geometry, and all that stuff. And then we have a variety in data model. I listed some example data models, grid data model, SWOT data model, point data model, and so on. And we have variety in data structure. We use list or Excel spreadsheet, the table, and so on. And we have also variety in data formats. And there's a list of different data formats there that we have to deal with. Now, the last one is grayed out because that's not something that our approach will address. So good scalability in variety will bring about much greater value. So our invention, our design, we designed this STAIR to address the scaling of a variety. STAIR stands for Spatial Temporal Adaptive Resolution Encoding. The details you have to find in either my publications or later presentations this week. STAIR stands for Spatial Temporal Adaptive Resolution Encoding, implements hierarchical indexing in both the spatial and the temporal domain. In spatial domain, it's based on the hierarchical triangular mesh, and in the temporal domain is a hierarchical cylindrical indexing, encoding. And given a precision then in both space and time, then every place on Earth and every time slice is indexed by a unique STAIR index, a pair of STAIR index. And all the Earth data can be indexed uniformly and universally. The best way to leverage STAIR is on the tightly coupled, is using the tightly coupled approach on a shared nothing architecture. Tightly coupled storage and compute, and with STAIR, then data placement are co-aligned spatial temporally. In other words, it doesn't matter which data set it's from, the same spatial temporal subdomain will reside on the same node. So all operation then requiring spatial temporal coincidences becomes pleasingly parallel because each node can handle just its own part. And for example, like validation, verification, when you compare data sets from different sources, and that's one example, or you want to find out the environment conditions of certain phenomena, and that will be another example. So that restricts data movements into confined it to the node between the compute memory and the local storage. CIDB is an example of a tightly coupled approach, and it supports not only multi-core parallelization, but also distributed parallelization. A loosely coupled approach then will have a hard time to match that performance given the same resources. Then the application of STAIR to existing file-based, file-centric practice will also provide value. So the summary is that making inference enabling connections require big data processing beyond what is defined here, deep learning, so to get it deeper. And cost-effective systematic data processing requires good variety scaling, and that's our primary contribution in the last few years. And STAIR can effectively scale earth science data variety and is best exploited on a tightly coupled approach using shared nothing architecture. And the parallelization can be also popularized through such a system, a platform, and STAIR can be adapted to existing data practices. So I'm going to show you some more, remind you of the other presentations here. And I acknowledge the funding sources for my work. And the next one is, while the run I can answer questions, is a prototype system that allows scientists to do interactive data exploration and data analysis based on the technique and the system that I had just mentioned. All right, thank you.
We have time for one or two questions.
So I like the concept of giving, I guess, a space and time address to all the points. Does the STAIR framework also have a way to incorporate information about the connectivity in space and in time? Since that connectivity information is sometimes really important.
Yes, yes, it does. And also, I didn't have time to elaborate, but we also implemented a connected component labeling, and to find for event, phenomenon. Basically, we connect the spatial temporal coordinates of a distinct event. So it's a spatial temporal entity. Say for just like Hurricane Katrina, it doesn't matter when it is. It's Hurricane Katrina because it's a connected thing. Yeah.
Okay, thank you. And this brings us to our last talk of this session by Matthew Hancher, who will speak on new techniques for deep learning in geospatial data using TensorFlow, Earth Engine, and Google Cloud Platform.
Which is my clicker? Right here. Okay, thanks everyone. Good to be here. So in contrast to most of the previous talks of the session where you learned a lot about some very specific applications or specific neural network structures and so forth that have been used, this is going to be a talk that's more focused on tools. And I think as the previous speaker motivated, it's going to turn out to be a lot about tools for data preparation and management, which does turn out to be a large part of the work that goes into training and applying deep neural networks. And I'm going to try to do a few things here at a high level. I'm just going to kind of motivate what we've been doing in the space at Google for a long time, some of the tools and techniques and applications that we have used, and then say a bit about both the tools that are in general availability today that you can use, some tools that we're in the middle of developing that we're looking for people to help test in the very near future, and conclude with a few thoughts about kind of where we're heading with our tools in the year ahead. So Google has been making use of deep learning in a wide range of areas for a number of years. Things started getting interesting back around 2012. We stopped, at least on this graph, kind of keeping track after 2015 because we shifted to a philosophy inside Google that basically if you're not figuring out how to apply deep learning to your problem, you're probably doing it wrong. We're using it all across the company for pretty much everything these days, most famously in areas like smashing the game of Go. Which as a Go fan I've been personally enjoying watching. And a part of that has been applying deep learning in geospatial and mapping related areas. So this we got started a number of years ago applying it to problems like what you see on the left where we're attempting to identify street numbers from Street View imagery. So it's fairly easy in many places to go and learn about the road network, but if you actually want to locate individual buildings, you have to know where on those roads they are, and sometimes the best way to do that is to actually read those numbers off the street signs. And so you can actually see on the sort of background image there are little, almost illegibly small street numbers on almost all the houses, and if you can do this in a sufficiently automated way, you can interpolate the few gaps and do pretty well. So this got us into the business of deep learning. We now use it all across our geospatial mapping work. On the right is an example from my own team, the project Sunroof, where we study solar residential potential. We use deep learning to understand exactly where the buildings are, exactly what the buildings are, so that we can then compute solar insolation and so forth. And just as a third example of this, with some partners of ours at SkyTruth and elsewhere, the Global Fishing Watch project takes a very different type of data. This is ship movement data from AIS transmitters on board all of the world's vessels to understand, using TensorFlow and deep learning, when ships are moving in certain patterns that correspond to various types of fishing activity. And we can use this to identify the standard shipping or other fishing techniques, and also in some cases identify illegal fishing activity where people are doing not what they said they were going to do or not where they said they were going to do it, and so forth. And you can see the little blue hexagons there. Those represent Google Cloud Storage on the left, Google Data Flow, which is a sort of large-scale, general deep data preprocessing tool, and then Google Cloud Machine Learning Engine on the right, where we run TensorFlow in the cloud. And I'll say a bit more about how that works as we go forward. All of this is based on the TensorFlow open source package, which we released in 2015. It's based on the years of work that we've been doing inside Google, developing machine learning models for a range of tasks. It fairly quickly became the #1 repository for machine learning on GitHub. This is the tool that we use primarily for that whole range of machine learning applications inside Google today. And it's one that we have now been shifting to understand how to make it easier to use in specifically a geospatial machine learning context. And that's really what I'll be talking about. We've heard a lot about, at a very high level, what you need to be successful in machine learning. A big part of that is large data sets, and in particular here, we're going to need access to the relevant large Earth science data sets. You need good models and a library like TensorFlow where you can easily implement those or share implementations in the open source community. And you need lots and lots of computation. You need that data and that computation close together. And so for all of these reasons, we've observed that deep machine learning is really made for the cloud. There are, of course, institutions that have access to large-scale, high-performance computing infrastructure themselves. Many folks are in this room who are in that category. Of course, many folks at this conference don't have access to that directly, and we're trying to provide that kind of capability in a cloud computing environment. One of the things that we can do in our fairly unique data center environment at Google, where we have a deeply vertically integrated data center where we can control and develop everything, we can bring fundamental advances in hardware to the table. So we've developed over the last several years what we call tensor processing units. These are specialized hardware for doing the kind of math that comes up in deep learning. So much as we've already found in the community that we can use GPUs to accelerate much of that math, you can go even further if you really hand tune the processing hardware for exactly that kind of problem, rather than reusing hardware that was designed for graphics or for kind of general purpose parallel mathematical computing. So one of these units here, that's 180 teraflops, I believe. We gang them up in packages of 64. That's it's in the petaflop range. And all of these we make available both to our own internal machine learning problems. And so, for example, if you were watching AlphaGo, Play Go, that's running on banks of TPUs, and we make them available through the Cloud Machine Learning Engine cloud program. All of that, kind of the way that we think about and the trends that we've seen in cloud computing represents a sort of gradual transition away from first the first wave of large-scale computing, which involved people buying and operating their own large-scale computing hardware, to a second wave, which is in many places still the dominant wave, which is based on virtualized computers. So you go to your cloud computing provider and we will happily sell you these. You buy virtual computers, you buy virtual storage and so forth. But it still fundamentally feels like a regular computing environment from phase one. We're moving to phase 3, the serverless world, where there are tools that allow you to show up and not worry about provisioning hardware, provisioning storage, any of that. You just show up with your data and your problems and go. And that's what we're really leaning in on in a number of areas. So within the machine learning space, you can go get the open source TensorFlow package. You can run it on your own hardware. You can run it anywhere. It's great for people who really want to explode and get into the insides and play around. But for most people who just want to show up and host or train models, the Cloud Machine Learning Engine lets you do that in a totally serverless way. And of course, if you just want to use some of our pre-built models without having to train any at all, we have a growing range available. In the geospatial domain, we're integrating all of these tools with the Google Earth Engine platform. So this is our cloud platform for petabyte scale analysis of geospatial data. It's been around for a while. In case you aren't familiar with some of the things that we've done with it, at this point we have thousands of users doing a range of things. You'll hear about it around the conference. But our first big example, which we talked about here a number of years ago, was taking the entire Landsat archive in conjunction with, this is really led by our colleague Matt Hansen and his team at the University of Maryland, and understood the forest dynamics at a 30-meter resolution globally over the full 21st century. More recently, led by a team at the Joint Research Center in Europe, We did the same thing for global surface water dynamics, looking down to now a monthly scale to understand how surface water is changing around the planet. These are examples, both of which were powered by machine learning in one way or another, although classical machine learning rather than deep neural networks. All of those kinds of capabilities are enabled by our public data catalog, which brings together hundreds of data sets, including things like the entire Landsat, Sentinel-1 and 2, et cetera, catalogs. This is petabytes of data that we have already done the drudgery of acquiring it and bringing it all into a kind of unified form. So you can just show up with your questions, your algorithms, and go without having to worry about the data preparation component. So these are updated daily with new imagery. In some cases, for some of the more timely data sets, updated sub-daily. And it includes everything from satellite imagery to weather and climate data, ancillary data sets like population data sets, existing labeled data sets that have been classified through other means, like the US Forest Service and USDA data sets, a wide range of things. And this public data catalog we grow based entirely on user request. So if you become an Earth Engine user, there's a area where you can submit your own requests and vote on them, and we'll do that drudgery of bringing them into the platform for you. Got a couple of interfaces people are using here. Our code editor is sort of like a traditional software development environment duct taped to a map, where you can very easily interactively explore new techniques and manage your data and your scripts. You can also drive all of this from a Jupyter or Python notebook environment, which turns out to often be very powerful for machine learning with TensorFlow, which is also well-driven from that kind of environment. Just a quick plug, because I get lots of questions about this. Any of the data that you process, bring into the cloud, generate in the cloud, you can bring that data out. That's your data, it's not our data. I just want to be very clear that that's a key aspect of this research platform. And one piece that we added this year that is especially relevant to this machine learning conversation is the ability to natively manage large tables of vector data, points, lines, polygons with arbitrary properties. This becomes particularly important as a way to bring label data of various sorts in and manage it and use it within that same framework. We also have a small but growing catalog of public vector data sets now, in addition to our existing catalog of raster data sets. So this gives you a few ways to manage your label data in Earth Engine. You can do hand-drawn data. You can use data with our sister product fusion tables, and now you can manage very large data tables in Earth Engine directly, upload a shapefile, et cetera. So when people are doing machine learning in Earth Engine, what are they really doing? They're taking their input data, which is managed in the platform, and labeled data. They're sampling them in various ways, and generating, essentially, virtual tables of data to feed into machine learning techniques. This is really designed for around up to, say, 1 million training features. And you can use these tools to slice and dice and generate your validation and test samples or do stratified sampling and so forth. And so, a couple of examples of things like randomly sampling from labeled raster data set or sampling within hand-drawn training polygons. These are all kind of one line of code to do that data preparation. And there are examples just on our public documentation for how to do these kinds of things. We have the sort of core set of classical machine learning tools, classification and regression trees, random forests, and so forth, that are all immediately available for you to use. And you can also, if you have an existing tool chain for classical machine learning, say using R, you can use them together. So, for example, you can train a decision tree using R and bring that, so R will generate a little text dump of your trained network, your trained classifier, and you can bring that into Earth Engine to apply it immediately to all of the data in that catalog. But the real fun happens when you combine Earth Engine and TensorFlow. So you can use Earth Engine to do your data prep. You can also use it for post-processing and visualization. And moving data back and forth is really where we've been working to improve the tooling. So today you can do it somewhat manually, and a number of users are, but what we're building right now are a couple quick new features that we are looking for folks to start playing with essentially immediately in the new year. So firstly, the ability to pull these image patches out along with the other data. So this is very common if you're training a convolutional neural network. And secondly, the ability to export that directly to a TF record file, which is a sort of standard file for pulling into TensorFlow training networks so that you don't have to do any additional transformation of the data. So here's a real simple example of pulling lots of labeled images of cars into a Python notebook where you can then pick up with whatever your standard TensorFlow training environment is. And then lastly, coming a little later, but we have prototypes working of as you get models that you have trained up and want to share, you can host those in Cloud Machine Learning Engine, and you will be able to invoke those, again, directly from within Earth Engine. So this is a real simple example applying a cloud model. So in closing, we're again looking at the sort of spectrum of users, from ML researchers, folks especially in this room who really want to focus on using TensorFlow hands-on, playing with new model techniques. That's where the data prep is particularly useful. As we work to the right, hosted models over time that are built by you that can be shared with others within that ecosystem. So, thank you.
Thank you very much. One short question.
Hi. You say you are going to release the labeled image patches. Then what about it? And can you provide more details? Is it rather high resolution images or?
So yeah, to be clear, what we're describing there is a tool that you can use to easily extract image patches from any data set. So that's not us producing a new label data set. That's giving everyone the ability to do that very easily within the same framework as everything else I've been talking about.
Okay, thank you very much.
Thank you.
This concludes our first part of this session. We will reconvene in 20 minutes after the coffee break for the second part. And enjoy the coffee.